Again, good afternoon, everybody, and welcome to those who may be watching on the recording. My name is Stephanie Lewis. I will be your moderator today, and welcome to another National Institute for Congestion Reduction webinar series um, uh, entitled DARTS, Drone-Based AI Research Real-Time Traffic Incident Detection System. It is my pleasure to introduce our four presenters today. We have Dr. Yuyu Zhang, who is a professor with the Department of Civil and Environmental Engineering at the University of South Florida. We have Mr. Joseph Post. He is a senior research associate, also with the Department of Civil and Environmental Engineering at USF. We have Dr. Bai Li, who is a researcher in the Advanced Air Mobility Department here at the Center for Urban Transportation Research. And finally, we have Dr. Achilles Cortelles, who is also a senior research associate and the assistant director of the Intelligent Transportation System and Traffic Operations and Safety Program here at Qatar. So with that, it is my pleasure to hand it over to Dr. Zhang. Dr. Zhang, take it away.
All right, thank you so much, Stephanie, for the introduction and for organizing this webinar. And welcome everyone to this webinar. And I'm really glad to present our work, which is based on the NISA project 4-3 corridor-wide surveillance using unmanned aircraft systems. So this is a multiple phase NISA research. Actually, what I present today is basically summary of the accomplishment and the research outcomes of the phase 3. And I want to mention at the beginning, we also collaborate with University of Puerto Rico at Maguez and with the team led by Dr. Crucci. And after he retired, I took over and became the PI of the entire project. So I want to acknowledge their contribution at the beginning of this project a couple of years ago. All right, so this is a nice picture of our team. And I will briefly introduce the team member from the left to right. So on the left, you will see Dr. Payson Lin, and he's in this project, he kind of participated and contributed to the project development. And we also have Dr. Achilles Curtis next, and he's a co-PI, and also he's one of our drone operators. And in this project, he actually led the drone procurement and the compliance and maintenance of the drones and experimental design data collection and also the reporting. And we have Mr. Joe Post. He's our senior investigator on this project, and he's a retired FAA employee, used to be the acting director of system engineering of the Next Gen office at FAA. So he's an aviation expert, and in this project, he looked into aviation-related parts, and he actually led the effort for the drone operation training so that our team members can get the drone operating license. And he also performed the airspace analysis while we select the locations for data collection. And he also actively participated in the field experiments. And for myself, Stephanie mentioned I'm professor in the department as well as leading the advanced air mobility program at Qatar. So I was in charge of project development management, communication coordination with US DOT and FDOT. And I also want to mention the young gentleman next to me, which is Mr. Brian Porter. And he's actually FDOT District 7 employee and pursuing the part-time master degree at University of South Florida during this project. So he's one of our drone operators, and he's also coordinate with the incident management team at the FDOT District 7, as well as a road ranger for obtaining the information of the accidents, crashes, and then go there with them to using the drone to collect the data, which is very important for the success of our project. And I want to mention Dr. Bai Li. He's our kind of main contributors to the algorithm development as well as the system development, which you will see later in our presentation. So he developed a learning-based algorithm and the platform, detection platform. And also he did a lot of data collection and field experiment. And last but not least, we also have another PhD student and participate in the training of the learning model. So besides all that you have seen from the previous slide, I also want to mention another two students. One is the Dr. Hualong Chang. He graduated a couple of years ago, and he contributed significantly to the trajectory traffic trajectory extraction algorithm. And another one is the Miss Cassandra Yao Chui. She's a master student from business school, and she actually helped a lot on labeling the data. We also want to thank FDOT District 7 Office, especially the Traffic Operation Office, and Regional Transportation Management Center, and also the Road Range Program for allowing us to go together with them to the crash site and using the drone to collect the data along the road. And also acknowledge the Florida 511 website provided by the RTMC of FDOT to provide the real-time traffic information that actually we used in this project. I mentioned about University of Puerto Rico at Marquez. I want to acknowledge Dr. Cruci and Alberto Figaro Medellin, and also Yvette Cruzado from that university for the collaboration at the early stage of this project. All right, so next I want to briefly introduce the background, objective, and also the research approach of this study. So we know that NISA is focused on the congestion reduction. And by doing that, we first want to understand what are the main sources of the congestion reduction. And the Office of Operations of FHWA actually defined the traffic incident as the number one source of the non-recurrent congestion. And the traffic incident not only caused the loss of life and the property damage, but also cascading the congestion to the upstream, and it may cause the secondary incidents, and it deteriorates the traffic conditions further. And some severe crashes actually could block, 2 or 3 lanes of the freeway and cause like hours of the stop of the traffic and quite a significant delay. So in terms of incident detection, there are several steps are very important. The first of all is the detection, how quickly we can detect the incidents without any false alarm. And then, of course, is understand the severity of the crash. And then the incident management teams can coordinate with other stakeholders to decide what are the resources needed to help clear the incidents. So in terms of detection, we do have some conventional detection methods. For example, we have highway patrol vehicles going around on the freeway, and whoever involved in the crash or somebody passed by, they could call and report the incidents. And on the other side, we also have CCTV cameras that can detect the traffic management center can rely on the CCTV system to detect the crashes and then come up with some clearance plan. However, there are some limitations of these traditional ways of incident detection. When we look at highway patrol, it really relies on the human power. So there's a coverage limitation, like not all the freeways having the highway patrol vehicles going around. And dependent on where they are, dependent on the relative locations of where the highway patrol vehicle is and where the incident occurred, it may delay the detection of the incidents. And also, this service is not 24/7, so the limited operational hours actually could reduce the efficiency of detection during the night hours, which is, for some segments, it's when the incident actually occurred more frequently. Another thing, of course, is technology limitations. It involves lots of intensive trainings for the road rangers to catch the advancement of the technology. And in terms of CCTV, some of the CCTVs have limited field of view, especially when the roadway has some significant curve. And also, many of the CCTV are like RGB cameras dependent on the lighting and also other conditions, like if there's a fog or rain, then the effectiveness of CCTV is not so good. And many of our CCTV system is aging, so it requires quite a lot of maintenance and maybe the replacement in the very near future. Another thing is, to transmit all the informations from CCTV to traffic management center, it requires lots of width of the data transmitting. So what's the benefit of the drone-based traffic incident detection? As I mentioned, the traditional one have some limitations. So for the system that we already have the CCTV coverage, but not so perfectly well, then the drone actually can kick in and play some supplementary role. And in some other roads that we do not have the CCTV or the coverage is not so complete, then the drone actually could play the important and the main role for flying around the segments and detect the incidents and provide the information to the TMC and the incident management team. So, and also in our project, we use the drones with the dual camera, which means one is the RGB camera, another one is the thermal camera. So why we want to do that is we want to avoid the privacy concern. So at the end, we use the thermal camera to capture the images. That is what you can see at the bottom, the right. And meanwhile, we have the RGB because we want to, at the early stage of our study, we actually collect both images and run object detection algorithm and compare the performance of while using the RGB images versus using the thermal images. And another advantage of the drone is the flexibility. So, drone can be launched anywhere. It's not fixed at certain locations, just like CCTV. So it's adaptable and also flexible. And in terms of coverage, the drone can fly. It's like a moving, or we call it mobile detection method. So it could cover more areas if it's needed. And it also could be cost effective. As I mentioned, our CCTV system is aging, and we probably need to replace them and upgrade them. And the cost effectiveness of drone may outperform than the CCTV system. All right, so what are our research goals and objectives? Now, as I mentioned, this is a multiple year research project. So the research goal and objectives now I present here is more focused on the phase 3. So in phase 3, the USF team aims to develop a drone-based AI-powered real-time incident detection system. Now, I already talked about drone-based, and AI-powered is more like we want to take advantages of the learning algorithms, learning methods, learning modeling. And in terms of real time is that we want to continuously transmitting the images from the drone to the ground station. And then our algorithms actually can process the images before another set of images coming from the drone. So by achieving that, we can continuously processing the videos and images and then give the real-time detection warning and outcomes to the practitioners. So in terms of objectives, we want to develop effective learning algorithm, computationally effective and running very fast. Another one is to develop software and consolidate the hardware for implementation of incident detection. So later you will see, we developed the web-based and also the smartphone-based software and also the user interface. Another one is we want to validate our developed system, validate its operability as well as efficiency. So what is our research approach? First of all, for this program project, we look into how we should collect the data by using the drone platform. So for doing that, first of all, we did the airspace analysis, make sure that the site where we collect the data actually will not intrude into the controlled airspace serving the airports around us. And another thing is we look into the crash data of our freeway network in our region, and we want to choose somewhere that has more frequent has crashes frequently occur. And another thing is that we look at the height of the drone, how high they should fly, 100 feet or 200 feet, 300 feet. We also look into the angle of the camera, should that's perpendicular to the center line of the freeway, or should it have a certain angle? So we actually did experiment design, come up with all different combinations of these parameters. And then we collected data, and then we run the images with the object detection algorithm and then compare the performance to see which combination actually will give us a really good outcomes. So after doing all that, we decide to use a certain height, maybe 200 feet, and also the camera perpendicular to the center line of the freeway. And then our speed could be 10 miles per hour or 15 miles per hour. And with the data, next step is the trajectory image generation. So we actually took the advantage of off-shelf Euro model, and then go from there. We developed our own trajectory extraction algorithm, which Dr. Bali later will describe it. And after that, we also applied the neural network learning model and to detect the crashes. So I want to mention that some existing studies try to detect the congestion, but we know the congestion could be recurrent or non-recurrent. So recurrent congestion could be caused by the increase of the flow during the peak hours, and it could be caused by the change of the geometry of the roadways, like the drop-off of one lane or the off-ramp in the merge of the vehicles from off on-ramp, etc., etc. But the non-recurrent condition could be caused by mainly like incidents and sometimes caused by the work zone. So our model is trying to detect the crashes, not only just the congestion. And Dr. Bali will elaborate this a little bit later. And after that, we went to develop the real-time detection system, so including the software or the smartphone app, and also the web-based GUI for the incident alert. And then eventually we went to the field validation. So we want to see if we can detect the incidents crashes real time. And also we want to compare the results with other conventional way. For example, we compare with 511 to see when, for the same incidents, actually when they got the reporting and they validate the incident. So we want to see if our system could be efficient and effective. So next, I will let Dr. Bai Li to introduce the algorithm.
Okay. Thank you, Professor Zhang, and good afternoon, everyone. I'm Bai Li, a postdoctoral researcher supervised by Professor Zhang. And next, I will focus on introducing the development and fine-tuning of the traffic incident detection algorithm based on machine learning methods. So I'll start with the vehicle trajectory extraction algorithm. The flowchart of the algorithm shows the algorithm begins by receiving a table containing coordinate information of the vehicle's center point from each video frame, as identified by the YOLO algorithm. It then tracks the movement of the centroid coordinates frame by frame using the LK optical flow tracker. This process creates a sequence that records changes in the centroid coordinates of each vehicle throughout the video. Considering the drone's fixed speed while capturing the video, the algorithm compensates for the offset in the vehicle's centroid coordinates caused by the drone's flying. And this compensation is calculated based on the timestamps of each frame and the drone's speed. The algorithm continues this calculation until it has processed the required number of frames for the vehicle trajectory extraction cycle. Then the algorithm extracts vehicle movement from the left to the right side of the video and compiles a time sequence list of vehicle center point coordinates. This approach ensures that the sequence of the vehicle trajectories corresponds to a single traffic lane direction, helping to mitigate issues arising from significant traffic flow differences in opposite directions. After processing, the algorithm saves the time series of vehicle centroid coordinates from the video to a final table for this computation cycle. It will also generate a vehicle trajectory image based on its sequences, providing a data set for subsequent training of the machine learning algorithm. And as we know, ResNets are advanced neural network architectures designed to address the vanishing gradient problem in deep networks by introducing skip connections that allow gradients to flow through a network directly. ResNet facilitates the training of much deeper network. This structure enhances the network's ability to learn and generalize from complex datasets, making it suitable for image classification tasks like detecting traffic incidents from vehicle trajectory images. And the core feature of ResNet is its residual blocks, where inputs are added to outputs, enabling the network to skip layers without loss of information, thus maintaining performance integrity even as the network depth increases. Modifications in hyperparameters such as layer depth, batch size, and data augmentation significantly impact the model's accuracy and adaptability. These attributes have positioned ResNet as a preferable model for complex image classification challenges and providing a robust framework for traffic incident detection from vehicle trajectories. In summary, here shows the results of the fine-tuned ResNet model performance. And when employing the ResNet model for traffic incident detection in our project, and several key decisions were made to optimize model performance. We chose grayscale images as the input format, utilizing a 34-layer ResNet model's network structure without data augmentation, and setting the batch size to 32 during the training process. These choices aim to achieve the best possible model training outcomes and to maximize the detection accuracy for traffic incidents. In summary, these parameters settings allows the ResNet-based model to achieve a peak test set detection accuracy of about 0.81, showcasing the model's enhanced performance under the chosen configuration. In addition to constructing the detection model using the ResNet framework, we also designed a detection model based on traditional convolutional neural network structure to further reduce model complexity and improve real-time performance. Firstly, the research problem of this project can be transformed into a picture classification task. CNNs are a cornerstone in the field of deep learning, particularly applied in processing data that has a grid-like topology, such as images. CNNs are designed to learn special features automatically and adaptively through back propagation, making them exceptionally adapted at image classification tasks. In this study, a convolutional neural network model is constructed to achieve the image classification task. The figure shows that the model contains 3 convolutional and pooling layers and 2 fully connected layers. The input of the model is the vehicle trajectory image in 50 by 56 by 56 pixels. The final output of the model is a 2-dimensional vector that is used to determine whether a trajectory image represents a traffic incident. After optimizing the ResNet model, we applied the same training and testing datasets to the self-designed CNN model. By comparing the 2 models, the one with the highest accuracy and the lower computational resource requirements will be selected as the fundamental model for practical application. During the training process, an early stopping mechanism was also implemented to prevent overfitting. Additionally, to investigate the impact of different vehicle trajectory durations on the CNN model's training performance, and to determine the optimal extract duration, we evaluated 5 different trajectory durations of 3 seconds, 5 seconds, 10, 15, and 20 seconds. Experimental results indicate that the CNN model achieved a prediction accuracy of 0.9 across all 5 different time durations evaluated. Among the different time durations tested, the 15-second vehicle trajectory samples achieved the highest detection accuracy on the test set, reaching up to around 0.95. Consequently, for the ongoing development of the real-time traffic incident detection platform, we will adopt a 15-second time duration for generating vehicle trajectory images from drone video clips. Compared with the CNN model, it is likely that the ResNet model suffered from overfitting, leading to its lower detection accuracy. Therefore, considering the simplicity and the efficiency needs of our project, we will utilize the self-designed CNN model as the machine learning model for detecting traffic incidents. Since the goal of our study is to develop a drone-based system for automatic real-time traffic incident detection, the real-time nature of the detection process is a key point to be considered. Results here show the algorithm processing time of only 8 videos, numbered 1, 3, 6, 7, 8, 10, 12, and 14, out of a total of 51 video clips, slightly exceeds the video duration. Examining the total duration of 8 videos, it can be found that the durations are all less than 70 seconds, while the processing time of all the video clips with duration of more than 70 seconds is shorter than the video duration. Therefore, in this study, 2 minutes will be chosen as the standard duration of the recording thermal video clips of road traffic flow to ensure the real-time processing of the algorithm. And next, Dr. Carteles will introduce the development of the traffic incident detection system. Thank you.
Thank you, Bai. Right now I'm going to present the system of how it actually worked after the implementation of the algorithm. So what we see here on the left side is the system in a schematic. We can see on the top left we have the drone, which is controlled by the remote controller and smartphone application that the manufacturer makes. The drone is actually connected to the controller, and also is as you can see in the middle there, we have a component called live deck. It's a second controller broadcast module where it receives the same information as a regular controller for the drone. Therefore, it has all the information needed, and we used it for mostly the video as a secondary input so that we can actually use it for our analysis. The live deck is also sending information to the via cellular network to a workstation where the system is running. And at the same time, it's also connected to the streaming platform so that we can actually stream the video in real time back to the workstation. And this is necessary because we wanted the detection to be in real time, and not only real time, but as Bai just explained, basically be done as the video is collected without any delay. So next I'm showing here the Android app, which is we're using the forward camera of the drone, GPS coordinates information to the video streaming platform. What you see here in the middle is the app that was developed that has controls for the drone, but also controls to send the video streaming to our workstation for analysis. Each box represents a different function, obviously, and the figure B there on the top right, as you can see, it actually has that's actually a camera footage, and because it's a thermal camera, that's why it's red. But the idea is that we're showing that there is actually output from the video that says that the functions are working after you start pushing the video to the workstation. And we're also collecting GPS information. So a user can actually make sure that everything is working as appropriate before they actually start their mission, so that they can, not fly and then have nothing, because that can happen. And on the bottom there, figure C, you see the information that the pushing has stopped. So therefore, if you actually finish your mission and you stop, you can hit the stop button, and then you see the messages that says, okay, I'm stopped. Next, we have the software architecture. We detail the software module on both the drone side and the workstation side. So the left is a drone side where, as you can see, we have the start-stop command on the application that I just showed before. And we start that way some background threads. Threads obviously are functions that start working on the in the app. So we have the GPS coordinates are collected, the video streaming, and obviously human HMI interaction. The GPS coordinates and the video streaming actually send information to the workstation side, as you can see, where they're collected and stored. And therefore, on this side, we can actually start saving the data and kind of start processing, which happens on the video processing thread. And therefore, we can actually control the whole process, having access to the workstation via the application, which is useful. Here we have the workflow of the signal detection system. On the left, we have the drone side again, and on the right, we have the workstation side. The software flowchart illustrates the software process on the drone. When the freeway incident detection begins, obviously after you press the button, the Android-based software first activates the drone coordinate transmission system, followed by the thermal camera live video streaming. While these two threads are running on the background, the software also receives commands from the operator in real time that you can actually stop the threads if you want. And therefore, it just monitors continuously until you decide as a user, I'm done with my mission and I'm going to stop. On the right, we see the workstation. So obviously, as we said before, we receive the information from the GPS and the video. We start processing the information that comes in, and we continue until again we end the mission manually with pressing the button on the application. This process is where the processing video there is where we cut the videos in 2-minute sections, and basically it's processing those 2 minutes and then continues on to the next ones. And that way we can achieve the real-time processing or close to real-time processing. Lastly, here we show the graphical user interface. So this is an application that was developed for. We can actually access it via workstation, so computer, or a smartphone. I'll show that later, that one. So for example, we have the information that was entered on the location where this is happening, on the highway information, the mission control. So you can actually control if you can start detection, pause it or stop it. On the right side of that second window, we have information that the processes are actually working as intended, and we have real-time detection results. Of course, those are a bunch of numbers. If you know what they mean, then you can understand that it's working. And on the bottom left, we have the real-time footage of the video as received. And as you can see, again, we use thermal camera. That's why it looks like that. The vehicles are light blue on the background, which is red because obviously the road is warm. And on the bottom right, we have the visualization of the detection, as you can see, and we'll go into detail a little bit more later. We see those dots that basically explain the red dots mean detection of congestion, and then the green that there is no congestion. And as I said before, this was also applied on the smartphone, so that because obviously for these operational characteristics of doing this in real time and in the field, obviously many of these things happen on smartphone devices. It could be a tablet or a smartphone. So this is what it looks like. The same application as I showed before. Instead of a computer, this is on a smartphone. Same functions, it's just obviously the format is different. So we have access to that on the field. And next, I will pass it on to Joe for the field test.
Thank you, Achilles. We conducted several field exercises to demonstrate the end-to-end operation of the system and validate the software. The exercise depicted here was conducted on 18 April 2024 at 4:30 p.m. local along the northbound lanes of I-75, just south of exit 279 at State Route 54. This location was chosen because of the regular weekday congestion, proximity to campus, suitability for operating the drone. For flying, we required a location off the highway, free of overhead obstructions, with the ability to maintain line of sight while flying a reasonable distance for the experiment along the highway. We always comply with the restrictions of 14 CFR Part 107, which are the FAA regs governing drone operations. This means that we have to stay outside of controlled airspace, no overflying of the roadway or people, and we have to maintain line of sight with the drone at all times. At this location, we were able to fly about 9,000 feet along the east side of the highway. The drone operated at an altitude of 200 feet and 10 miles per hour, moving in the direction of traffic. Fortuitously for us, but not for the occupants of the vehicles, a rear end collision occurred during the field trial within view of the drone. We have a little video here embedded. All right. So we extracted 3 experimental results from the April 18th demonstration for presentation using the historical review function of the detection control software. We show the results from the 3 flights along I-75 here. The first flight on the left at 4:48 p.m. was before the incident. You can see the typical recurrent congestion beginning to develop upstream of the highway exit. Recall the algorithm processes 2-minute overlapping video segments every 40 seconds. So each dot each dot is 40 seconds apart. A red dot indicates congestion. The second flight in the middle occurred at 4:59 p.m. The crash was detected at 5:02 p.m. The detection results text, which is cropped up here on the top of this image, indicates that the incident detection in red font. You can see the congestion developing upstream of the crash site with no congestion downstream. The final flight was at 5:11 p.m., showing extensive congestion propagation upstream from the incident. We can also display the recorded video from the history review page. The left-hand image was captured during the first flight prior to the incident. The right-hand image captured during the second flight, clearly depicting the crash. When the software detects the incident, lets the operator, she can click on the specific location and view the recorded video. After the field experiment, we obtained information about the crash from the Florida 511 website. According to Florida 511, a 2-vehicle rear-end collision occurred just before exit 279 on I-75 at approximately 5:09 p.m. CCTV video from the website reveals that a red sedan rear-ended an SUV in the right-hand lane. According to the Regional Integrated Transportation Information System, the crash caused congestion for more than 5 miles upstream, with the congestion persisting until approximately 7 p.m. All right. I thought we had one more slide, but obviously we don't. So I'll hand it over to you for our conclusion.
Thanks, Joe. Yeah, so finally, I will summarize our findings. And, we have developed a drone-based AI-powered real-time incident detection system. And as I explained earlier, the drone actually can provide flexibility and a robustness compared to the pole-mounted visual camera of CCTV system. And the neural network-based learning ensures that our algorithm can accurately detect incidents rather than predict them. We know that in current market, there's some algorithm claim that they can predict the incidents and crashes, but the thing is that there could cause a false alarm. But for us, we didn't detect any false alarm. So the accuracy of our detection is superior. And it can be, it's scalable, and also it can be adapted to different sites. And we talked about real-time capability of our system. So we can continuously transmit the video and process the video and come up with the results. And through our projects, we integrate both hardware and software components, including smartphone app and the web-based GUI that can be used by the traffic management center employees. So by using the thermal camera, which demonstrated the efficient detection outcomes, we could effectively avoid the privacy concerns associated with the visual imagery. Now, what could be the next step of the project? The system that we developed could be used by the different traffic management centers. Now, of course, we need some enablers for the deployment. For example, the protocol for drone applications in freeway incident detection and management. Actually, at the beginning, phase 1 of this project, USF team worked with the team from University of Puerto Rico, Marquez, and worked on the protocol. Now, of course, with the policy and the regulations advancement from the government agency like FAA, the protocol could be updated and refined, and then it could be used by the translation agencies while they considering deploying this incident detection system. Oh, sorry, I didn't put my camera on. And of course, we also need maybe additional hardware at the TMC if they're not already there, like, for example, the powerful workstation to run the neural network modeling. Another one is a personal training. Like in Florida, I know we already have, when I say we, I mean FDOT, already have a fleet of the drone and trained the FDOT employees to operate the drone. And as a manufacturer, the Brian Porter that I mentioned, who's a part of our team, now is kind of the guru in the FDOT on the drone operation. And another thing is we are open to any collaborations with translation agencies within the state of Florida and beyond. And we could perform more regional specific data collection. We can do more field testing, and then to train the model again so that the model could work for that particular region. And another thing is we are in the process of developing the user manual of the system that we developed, and then we actually can provide the personal training for the agencies who are ever going to deploy the system and help them to operate the incident detection system in their daily operation. So how about in the future? We have been closely observed what's going on and also the advancement in the drone manufacturing industry. As you can see from the right side, the Skydo is a company that they're developing this station plus drone. So that station has lots of functions that can have the drone automatically take off and then land. And imagine in the future, you could have a bunch of this kind of station along the road and then play as robots for the data collection. And the data collected from this drone can transmit it to the system that we have developed. And then we can give the real-time alert to the traffic management center if there are any crashes occurred on the segments that these drones are monitoring. So in summary, in the future, we expecting multi-drone based and AI-powered autonomous system for the traffic monitoring and incident detection. So with this, I'm going to stop, and I want to thank again for you to attend our webinar, and we open floor to any questions. Thank you so much.
Thank you so much, everybody, for all of the great information on the project. I did want to remind everybody that they can ask and submit questions by either utilizing the chat and or the Q&A box. We did receive a number of questions during the registration process. We'll start with the first one. It says, what were the biggest challenges in developing the system during the project?
I'm sorry, Stephanie, I was looking at the meeting chat. I was reading Hualong's note.
That's okay.
Could you please state the question again?
Yeah, absolutely. What was the biggest challenge in developing the system and during the project?
Okay, the first challenge was the data collection, because very recently, Bai and I, we went to attend the Informs conference in Seattle, and we took that opportunity to visit University of Washington and did a presentation there. So they were amazed by how much data we collected and how we can collaborate with our FDOT District 7 office, especially the highway patrol, road ranger, and then go with them together and collect the data right after the crash occurred. So I think that is quite challenging for many of other research teams. If we didn't have the significant support from the District 7, as well as having Brian Porter on our team, we might not be able to achieve that. So that was one challenge. And of course, another challenge is to achieve the real-time processing of the image. And the Bai actually spent a lot of time and effort to make that happen. So he only put on 1 or 2 slides, but that is like a month of effort, to improve the parameters, to run lots of, try and error, and to see how to improve the the performance of the learning model and which learning architecture could fit the needs of our project. And of course, other challenge is the validation. So we were very lucky, we did a validation, and luckily that we captured the incident during our field experiment for the validation. So I think all those are the challenges. That's why I was reading Hualong's notes, and I can echo what he said. Yeah, we started several years ago as a first phase 1, step by step, and we're glad to get where we are right now. Thank you.
Thank you. Yeah, I'm very familiar with that interchange there on 75, and it doesn't take long for an incident to back up that entire area. So the next question says, how can this system be scaled up to include multiple drones or in multiple regions?
Let me first touch on the multiple drones. So we actually looked into that, and we even had a white paper sent to FDOT and to see if we can take advantage of some US DOT funding programs. So we will continue the effort by working with our local agencies. So our vision is in the future, like a future project, we can acquire the Skydo or other companies' drone stations plus drone, and then we can work on how to coordinate the operations of the drones. Like me and Bai, we actually discussed on if we release the multiple drones and cover continuous segments, but if one of the drones actually detect the incidents, we could either let that particular drone hover around and detect more details of the incidents or car crashes and transmit information back to the traffic management center. But meanwhile, we need to have additional drone to back up and continue monitoring the assigned segments. So there are some open questions on how to control the multiple drones coordinatively, and then how how to handle the transmitting of the large set of the data transmitted from the drone to the system that we have developed. So we may need very powerful stations to process all the information. So there are different challenges, but I think it could be potential because we are facing the shortage of the workforce. We're also facing the aging system that needs to be replaced. So hopefully this advanced technologies could be helpful, and with the system that we have developed, they could work together to achieve the automated incident detection.
Great. And then the final question says, are there any modifications identified that can improve the system's detection and response?
So far, I think our model, the algorithm that we developed worked very well compared to existing like other tools that we could see from the published journals or public available document. So what could be improved? We were thinking that, we tested in Florida, and for other different terrain, like maybe in the mountain or something, the drone operations could encounter different challenges. So we haven't looked into that and thought more thoroughly about, what needs to be adjusted if we are encounter that kind of challenge. So yeah, another thing is the machine learning. We're seeing the advancement of the machine learning. So potentially in another 2 or 3 years or 5 years, the neural network learning model could be advanced from the field, and then we can implement those in our model and maybe achieve even better computational efficiency and performance.
Great, thank you. I did put the evaluation on the screen for those that you can either click on the screen or click on the link in the chat box. The feedback provided is not only important to our presenters, but also to the entire NICER webcast series. Before we end, it looks like we just have a few minutes left. Did anybody have any final thoughts or anything they would like to say to wrap up today's presentation?
On behalf of the team, I just want to thank Stephanie for organizing this NASA webinar and thank everybody participating and attending this presentation. There's a good news I want to share everyone is that we submitted a paper to TRB. And this morning, actually, I got an email from the committee chair of the Standing Committee of Intelligent Transmission System of TRB. And they informed us that our paper actually got a Best Paper Award from their committee. So that's very encouraging, and I just want to share with everyone. And I think that's the conclusion from our side.
Congratulations. That is fantastic news.
Thank you.
You're getting lots of applause. So again,
Thank you so
congratulations
much.
on that honor. So just a quick note, our next NICER webinar is scheduled for next week on November 7th. That title is Supporting Transportation Professional Growth Through TDM CP Certification. Our two presenters will be Sarah Hendricks and David Strauss. Again, the link is available there on the screen, as well as if you visit the homepage of the NICER the NICER website. So on behalf of the National Institute for Congestion Reduction, thank you so much for joining us today for today's presentation, and we'll see you all next week. Bye, everybody.
Thank you, everyone. Bye-bye.
Great job,
Bye.
everybody.
Thank you.
Thank you. Bye-bye.
Thank you. Bye-bye.